Hi, a very good afternoon to everyone in Singapore and the region. And to the other participants from around the world, good morning or good evening. It is a pleasure to share this event. Today, my presentation is on integrated use water management case study of Jurong Water Reclamation Plant. There are 4 parts to the presentation. 1, introduction. 2, use water treatment processes. 3, management of greasy waste. And finally, 4th, technology development. First, an introduction to the integrated water management in Singapore. It is based on the systems approach, where PUB, as a national water agency, manages the entire water loop, from stormwater management to collection of rain in drains and reservoirs, to treatment to potable water, and supplying to the population and industries. Thereafter, used water is collected in sewer networks, treated at the water reclamation plants, and then reclaimed to produce new water. Majority of the new water is supplied to the industries for non-potable use. A small amount is blended with reservoir water for indirect potable use. There is also desalination as another source of water. Today's session, we will focus on the water reclamation plant, as shown here in the figure. There are 3 principles for sustainable water supply. First, to collect every drop of rain that falls on Singapore. Second, to collect back every drop of used water. And third, to recycle every drop of water more than once. This slide shows the current water reclamation infrastructure. Since 2001, all our used water treatment facilities were renamed as Water Reclamation Plant or WRP. The naming was to convey the message that water is not just precious, it is a resource that can be reclaimed and reused. Currently, there are 4 water reclamation plants: Kranji, Jurong, Ulu Pandan, and Changi, which is part of DTSS Phase 1. We have briefly mentioned DTSS in the previous slide. Now, DTSS stands for Deep Tunnel Sewerage System. The idea was conceptualized in the mid-1990s, and Phase 1 was completed in 2008. It is like a superhighway for the conveyance of used water. The DTSS is part of the strategy to collect every drop of used water for water reclamation. Now, the DTSS provides a more sustainable solution in the long term. The benefits of DTSS include: 1, it is a more cost-effective option compared to expanding and renewing existing used water infrastructures. 2, as the DTSS works entirely by gravity, it eliminates the need for pumping stations and free up land used for WRPs, buffer zones, and pumping stations. The land free up can then be used for other developments, and also the plant, here in this case Changi WRP, has a compact design that is about 3 times more land efficient compared to a conventional WRP. And third, it is more robust and reliable in terms of operation. Finally, by co-locating the WRP with the new water factories, it ensures sustainability of new water supply. Now, this is an aerial view of Changi WRP that was completed as part of DTSS Phase 1. Here you see that the Changi WRP is currently the largest water reclamation facilities in Singapore. Upcoming is the Tuas Nexus project as part of DTSS Phase 2. After completion of the Tuas WRP, Ulu Pandan and Jurong WRP will be progressively decommissioned. The Tuas WRP will be an advanced treatment plant that is robust and reliable, energy efficient, space efficient, and will require less manpower to operate and maintain. Under this project, the WRP will be co-located with Integrated Waste Management Facility, or IWMF. There will be synergies between the 2 facilities. The IWMF will receive and treat municipal solid waste, food waste, recyclables, and dewater sludge, producing electricity, heat, ash, used water, and recyclables. Whereas the WRP will receive and treat used water, producing biogas, sludge, and water. Scheduled to complete in 2025. The Tuas WRP will also have one of the largest MBR systems in the world. Next, we'll go on to the used water treatment processes with the focus on Jurong WRP. This slide shows the aerial view of the Jurong WRP. The plant is located in the western part of Singapore, and it was built in phases. It comprises phase 1 that was completed in 1981, phase 2 completed in 1988, phase 3 in 2004, and phase 4 in 2018. Now, the plant's catchment includes both domestic and also high-strength industrial use water, and it covers a wide range of areas such as Tuasville, Pioneer, Benoi. And for the domestic catchment, it covers areas like Jurong West, Jalan Bahar, and parts of Bukit Batok. A typical daily incoming flow to the plant, about 40% is from industrial source, and the remaining 60% is from domestic source. Now, the plant has 3 key functions. 1, environmental protection by treating industrial and municipal use water to the required standards. And 2, reclamation of industrial water for reuse with membrane bioreactor technology. And 3, treatment of greasy waste. The plant has conventional use water treatment processes. For liquid stream treatment, raw sewage or influent use water enters through the core screen, through the pumps, and then to the fine screens, the detritus, primary sedimentation tank, aeration tank, and final sentiment tanks. It is then treated and purified effluent is then discharged to the sea. For solid stream treatment, waste activated sludge is thickened by flotation and screw thickness. The sludge is then fed to digesters, and after digestion, the stabilized sludge is dewatered and sent for incineration. Now, biogas, which is a byproduct from the digestion process, is then gainfully consumed by gas engines for in-plant power generation. What is not shown here is the new sludge treatment technology called thermal hydrolysis process, or THP. It was installed as part of the plant's phase 4 expansion. The THP is able to enhance anaerobic digestion and manage the additional solid load that is from phase 4, and hence avoided the need to construct an additional digester. Now, a key function of the plant is also to treat and produce industrial water from used water of domestic source. Since 2014, phase 1 treatment facilities at the Jurong WRP have been converted from conventional activated sludge process to an MBR plant. Now, this full-scale MBR plant has a treatment capacity of 15 mgd. It is to treat domestic used water and produces high-quality filtrate water suitable for reuse as industrial water. The industrial water is then supplied to industries on the Jurong Island for non-potable water use, typically for cooling applications. The MBR plant has a 3-stage process, anostic, anaerobic, and aerobic, that is able to concomitantly treat for removal of organics, nitrogen, and phosphorus. The plant is able to treat for phosphorus to meet industrial water requirement through the enhanced biological phosphorus removal, or EPBR in short. Just some elaboration on the enhanced biological phosphorus removal, EPBR. Now, from the microbiological perspective, there's an ongoing competition between 2 groups of organisms, known as the PAO and the COW. Now, the PAO stands for phosphorus accumulating organisms, and the COW stands for glycogen accumulating organism. How the PAO works is that in used water containing phosphorus, now shown here as phosphate, and organic source, shown here as VFA, the PAO will uptake the VFA to synthesize PHA and releasing phosphate into the waters. In contrast, in the subsequent aerobic phase, the PHA will be oxidized with the uptake of phosphate and release of energy. Hence, in this way, there is a net removal of phosphorus from the water. As more phosphorus is taken up in the aerobic phase than is released in the anaerobic phase. The phosphorus is then removed from the system through the waste-activated sludge. The GAL, on the other hand, it is not able to remove phosphorus. However, it will compete with the PAO for the VFA. And the challenge here is that typically there is faster rate of VFA uptake for GAL than PAO in warm temperatures. And therefore, for EBPR to work, we have to suppress the growth of GAL and select for the PAO, that means for the PAO, with the right operating parameters. These slides compare the MBR product water quality with conventional effluent quality as well as typical industrial water quality. It can be seen that the MBR product water quality is well within the guideline for industrial water. And for further information, it can be found in the below reference paper. Now we come to the management of greasy waste. Now, recently, the topic of greasy waste has attracted an interest. It was reported by 2 mainstream newspapers, both the Straits Times and the Zhaobao. The report cited that greasy waste treatment capabilities are set to increase in line with projected population growth and rising number of eateries. Now, some background on greasy waste generation and collection. First, food preparation and eating establishments generates greasy waste which contains fats, oil, and grease. Now, the greasy waste is first physically separated through a grease trap, as shown here. The grease trap is owned and maintained by the premise owner. The separated greasy waste is then collected by licensed collectors using tankers, and this is transported to and discharged at the WRP. Currently, Jurong is the only plant that receives and treats greasy waste in Singapore. This slide shows a step-by-step process schematics. After greasy waste is collected by tanker from the grease trap of an eating establishment, it will be transported and discharged at the greasy waste receiving facility of Jurong WRP. Now, the greasy waste collected from the tanker is generally pale grayish in color. You will see here on the slides. It looks a bit like the local barley drink. Now, and there can be significant variation due to the nature of the greasy waste, depending on the type of food establishment and whether it is a restaurant or hawker center and so on. The first stop at the plant is the discharge bay. Here, operators check that the tanker seals are intact before breaking them. Greasy waste is then piped from the tankers into a pre-treatment facility. At the pre-treatment, greasy waste goes through two chambers. First, fine screens, which filter out large debris like rags, tissues, and wet wipes, followed by grit remover. Next, dissolved air flotation. Now here, dissolved air in the form of micro air bubbles are pumped into the waste stream, attaching to the grease particles. Now, due to buoyancy force, the grease particles will rise up and get concentrated as a layer at the top of the tank. This surface layer is the concentrated greasy waste. If you look here in the pictures, it looks just like a milky, creamy milk tea. And then this layer is then removed via scrapers. Next, the mixing tank. The concentrated greasy waste is then mixed with used water sludge here. Then at the digesters, the greasy waste will be co-digested together with used water sludge to generate biogas. The biogas, which contains methane, is converted into electricity using gas engines for in-plant power generation. Now, this slide shows an aerial view of the greasy waste treatment facility at Jurong WRP. And finally, technology development. Now, the plant collaborates with research organizations and industrial partners in carrying out R&D and test bedding projects for technology development. Our approach is step-by-step from fundamental research to pilot and validation studies, demonstration testing, and finally implementation. Some of the technology projects at Jurong WRP include investigation of the carbon transformation and potential impacts of thermal hydrolysis process. The collaborator for this project is NTU. Next, we have evaluation of new generation ceramic membrane for industrial MBR. Collaborator is from the industry, Maiden. On the bottom left, durability of polymeric membranes in MBR for industrial used water treatment. This project is coordinated by NUS and included industrial partners such as DuPont and Tritech. And on the bottom right, demonstration of a self-adaptive process control technology for optimization of a membrane system for industrial used water treatment. Collaborator is industrial partner IntelliFlux. And there are other projects. Now, the technology development is part of the effort towards achieving environment and water sustainability. The priority will remain to be water reuse driven and to increase water recovery. Next, it is to reduce the use of resources and at the same time to recover resources, including land, energy, and chemicals. Finally, it leverages technologies to enhance operational reliability and efficiency. So with that, thank you. I have come to the end of the presentation. There is also a video about the plant, which will complement this presentation. Happy viewing.
Welcome to the Jurong Water Reclamation Plant. JWRP performs three core functions, namely treatment of used water to produce effluent for discharge to the environment, reclamation of industrial water using membrane bioreactor technology, and the treatment of greasy waste. The used water treatment process begins with conveying used water from homes and industries through the sewer networks to the plant's influent lift stations, or ILS. At the ILS, domestic used water is lifted up to Phase 1 and Phase 2 treatment facilities, whereas industrial used water is lifted up to Phase 3 and Phase 4 treatment facilities. Influent used water is first sent to the coarse screen shaft, or CSS, where large debris greater than 100 mm are removed. Used water is then conveyed by the main sewage pumps to the inlet works, where fine screens remove small debris no bigger than 6 mm, and followed by grit removal at the detroiters. After the detroiters, used water is conveyed to the primary sedimentation tanks for primary treatment. At the primary sedimentation tanks, or PSTs, heavier suspended solids in the used water settle to the bottom of the tank. The settled solids, known as primary sludge, are then removed from the PSTs and sent to the solids treatment stream. After primary treatment, used water from the PSTs is then channeled into the aeration units for secondary treatment. In the aeration units, naturally occurring microorganisms in the form of activated sludge break down impurities and organic matter as used water flows through the bioreactor tank in a plug flow mode. In the conventional liquids process, treated used water at the bioreactor, now full of microorganisms from the aeration units, then flows into the final sedimentation tanks, or FSTs. Here, settled microorganisms and pollutants are removed as waste-activated sludge and separated from the liquids. The clarified water, or secondary treated effluent, then exits the used water treatment process through effluent outfall facilities, where it is discharged to the sea. In parallel, at the solids treatment, sludge removed from the liquids process is converted to methane-rich biogas in the anaerobic digesters. This biogas, converted by gas engines into electricity, is used for in-plant power consumption. Following the anaerobic digesters, digested sludge is then dewatered by centrifuges before it is trucked away for incineration and disposal. One of the many key highlights of Jurong WRP is the greasy waste receiving facility. Biodegradable oil and greasy waste from grease traps found at eateries and food centers are tankered and treated here. Another key highlight is the plant's membrane bioreactor, or MBR treatment facility, which produces high-quality, solids-free industrial water for supply to industries on Jurong Island. The MBR has a 3-stage bioreactor configuration that allows for contaminant removal of nitrogen, phosphorus, and organics. Through enhanced biological phosphorus removal, or EBPR, Jurong WRP has been successful in reducing chemical consumption significantly in meeting phosphate requirement. Jurong WRP's Phase 4 expansion project, which was completed in 2018, avails the plant to new liquids and solids facilities for the treatment of industrial used water. As part of the project, Phase 4 is set to incorporate various technological enhancements on site that include lamella plate PSTs, equipped with an automated cleaning device, and airfoil turbo blowers for aeration. The Phase 4 expansion project will also see the installation of the thermal hydrolysis process, or THP facility. The THP facility aids to increase solids treatment capacity at JWRP without the need for constructing an additional digester. The THP will also enhance digester performance and significantly reduce digester footprint required for sludge management. JWRP is also home to many R&D as well as test bedding projects. These projects are aimed at developing technologies to achieve water sustainability by improving water reuse and enabling more efficient use of resources that include land, energy, and chemicals.
Well, thanks so much for that. In the interest of time, we've got quite a few questions here. I'm just going to pick out the first one that came in, and the other ones I will get answered offline, and the emails will be sent around to everyone in attendance, so they will all be answered. So the first one, Winson, that came in is, will the wastewater plants in Jurong specifically and in Singapore in general, is it managed privately with companies such as Everbright Water, or are they government agencies, or is it both in kind of a private government collaboration in terms of the actual management of these facilities?
All right, thank you for the question. So for these questions, the plant is being managed by PUB. PUB is a national water agency, so it is a government body. So to this question, it is being managed by PUB.
Brilliant.
Government, yeah.
Thanks very much. Yeah, there's some of the really good ones in there, but yes, they will be answered offline and sent around to everyone. So thanks very much for a really great presentation, Winson, and I'll hand over now for the next speaker. Thanks very much.
Yeah. Maybe I can just answer one more question. In fact, the first question about treated water in Jurong, why is it to see instant recovery? Actually, if you listen to the presentation, we have one phase one, which was actually recovering water for industrial water. So we use MBR technology to reclaim this water to industrial water standards. And this industrial water is being sent to the industries for non-potable use. So there is some form of recovery.
Right.
Right. So
thanks very much.
There's one question on used water, and that's true. We use used water instead of wastewater to show that water is a precious resource that can be reclaimed and recovered.